All right, so the task today, we're going to use Euler's method. We're going to be solving differential equations still. We'll give you the theory and then see if you can apply it. In your notes, I want you to go to this page right here, and we're not going to use this page. We're going to do something a little different. So you can go ahead and cross this whole chunk out. Flip your note packet over. I'm really going to try to give you a better visual of what you're doing. Most of you, if you understand what you're doing, you won't have to rely on your memory. So I've said our biggest task in here is retention, trying to retain everything from Calc 1 September all the way through Calc 2 in April when we're done with series. And the fewer things we can memorize, the better. So although my method is going to look different than if you Google Euler's method, it's going to be like a big strung out expression that you're not going to remember. I'm going to give you more of the process, and we're going to do it in a table fashion. It really does help. What I want to do first, though, is give you a concept of what you're going to be doing before we do it. So it's called Euler's method is because he's the one who came up with it. We are basically going to be doing, put on the back of your sheet, something similar to what you did in Calc 1. You are going to be having some spot on a curve. I'll call that C. And boom, you're going to be anchored on a curve, and they're going to tell you to use that location to estimate what happens somewhere else on the curve. So in a real-world situation, you will be given a differential equation and want to know what actually was there at some point, but maybe you can't fit a math model to it. So you do what's called an estimate. In Calc 1, we did what's called a tangent line estimation. So they'd say, okay, if this is what happens at 2, use the tangent line there to estimate what happens at 2.1. Do you remember doing those? And so you just get an equation for the tangent line, plug in a 2.1, and it would be a fairly good estimate. It'd be a little over because this is concave down, but it's really a poor process. Like that's not a very good process because what has to be the case? Like what do you have to do in order for it to be an okay estimate? Like when would it not be a good estimate is a better question. When you're far away. Yeah, the only time that tangent line is really very helpful is when you stay really close to it. That's why they always say to estimate what happens at 2.1 or 2.2, because out at 7, that thing's horrible. That line is going way up there. Maybe the curve even went down. Like there's such a margin of error. So what happened historically is Euler said, well, don't stay on that tangent line then. He said there's no reason why you have to keep walking basically on that tightrope. Yeah, there's a tangent line, right? Go ahead and draw it. Yes, there's a tangent line right here, but there's nothing preventing me from hopping off of it at any given time and saying I'm going to readjust. And the slope of this tangent line is the derivative, and as you'll notice, this slope up here is getting like super steep, and this one's actually approaching 0, and the slopes are way off. So what he did is he said, okay, let's go over and stop. Okay, and let's make an adjustment. And he called this like delta x. Some books call it h, but it's really just a step. It's like you're walking along that tangent line, but as you do so, you're getting more and more and more and more and more inaccurate. Does that make sense? So he said, I'm going to stop, hop off the tangent line. And what I'll do is hop off at this point, and I'll have an amount over I went up, right? So he moves over a certain amount, moves up a certain amount, and then stops, and then readjusts the tangent line so it matches the curve and walks along this one. So stop, readjust your tangent line, right? And then walk on that tightrope for a little while. And then stop, readjust your tangent line, and walk along that one. And you're much better able to follow the curve if you can stop and keep adjusting your slopes. That's the theory of it should make sense, right? So instead of heading along one tangent line, really what Euler's does is it hops on and follows tangent lines along the curve and just keeps basically, I mean, for lack of a better word, jumping on a better tangent line. So mathematically, we're going to figure out how do I jump off of this onto a better tangent line. That's what Euler's method does. So its theory is pretty cool. If you use it correctly, you get a much better, like if I'm right here, that's way better than if I'd followed along on the original tangent line. So the adjustment tweaks it. That's still not as good as we're going to get. When we get into series, what we do is, I'm going to give the sine wave right here. This sine wave, yes, I could hop on from Calc 1 and do a tangent line approximation. Horrible right here, right? Like super bad. Euler would say, well, hop on, but then follow this and then follow this. So his is a little better. But actually, lines aren't even a good way to follow that. If I fit a parabola right here, wouldn't I be really good in this little lobe? Right? And if I did a cubic, I'd be really good in this lobe. And if I did a quartic, I'm really good, right? When your calculator is programmed and you go to it and you're in radians and you do like the sine of 37 degrees, let's say, how does your calculator know what that is? It doesn't. And it hasn't been programmed because I could have done, let's say we're in radians, I could have done sine of 1.476521 radians. My calculator will give me an answer. Not because a computer programmer has programmed all the possible angles in, but because a computer programmer has fit a polynomial to the sine wave and programmed the polynomial in. Does that make sense? So when we get into series, we're going to have a polynomial that wraps the sine wave perfectly from negative infinity to infinity. Perfect. So that's what's programmed into your TI-84, so that when you hit sine of 11, it plugs an 11 into a preset polynomial. It doesn't have its sine programmed. Do you see what I mean? So in our series, we're going to be able to kind of wrap and curve around. Today we're not. We're walking straight, hopping off, walking straight, hopping off, but we'll eventually get a polynomial for that. It's going to be this. You're going to say, where does that come from? It has a pattern to it, and this is what's programmed into your calculator when you evaluate the sine. Notice the powers are odd. What do you notice about the sines? They're alternating. If you were to go right now and do this on your calculator, sine of 1, write it down, and then put 1 into this polynomial, they'll be the same. Okay? That's later. But today, we can't curve. We're just going to walk on really straight lines. So back to your notes. I want you to take a minute and just read this. It's basically what I just said. I screenshot this off the internet. He's a really cute-looking guy, Lenny. I'm kind of attracted to him in a strange, weird way. Not just kidding. I'm totally kidding. I'm recording, too. Oh, great. For all of YouTube to see, yeah. LaRue has a thing for Lenny Euler. He's got a little funk going on with his eye, too, right there. It's like one smaller than the other. Go ahead and read it, though. I just basically told you the general gist of what I got when I Googled images of Leonhard Euler. I found this guy with a nice little excerpt of what I just said. It's nice to have a visual of the guy, right? Pop your hand up when you're done reading it. If you are watching these, go read that paragraph and just make sure it makes sense. That ought to be enough time. So you need some stuff to get this started. I'll give you the minimal amount of machinery you need to make this work. First of all, you need to be told where you're going to hop on the curve. Okay? There's going to be some curve. You need to be told where you're going to hop on. We call this an initial point. You need an initial point. Sometimes it's handed right to you, and that's actually 90% of the time they'll say, f of 2 equals 7, so you've got 2 comma 7. Or they'll say using an initial value of 0 comma 4. They usually will tell you that. Sometimes, and twice on your worksheet, they do what College Board does, which is they hide things on a table. So they might have a table of x, f of x, and f prime of x. And the only f of x you have is this one, and then these are all empty, so you know that you have to hop on at 3, 7. So your point might be hidden on a table. You all right with that? Otherwise, the point's free. Next thing you need to be told is, I told you you're going to be walking along those tangent lines. You need to know how steep they are, and that's their slope and that's their derivative. So you'll be given the differential equation, and that's what our unit's on is differential equations. So dy dx will be given to you in terms of x, in terms of y, or both. It might say dy dx equals x to the 4th plus y, or 2x minus y, or what might frustrate you the most is one that you could actually solve by other means. Like if it's dy dx equals x squared, I don't need Euler's method to approximate what happens on the curve, correct? Because what's the antiderivative of that? Y would be what? X cubed over 3 plus Carl, and if they gave me an initial point, I could find Carl, and then I actually have a model for the curve itself. So some of them are going to frustrate you, but the minute I go like this, you don't know how to solve it anymore, right? It doesn't separate. It's got both of them over there, so you would be forced to use other methods. This is just another method for estimating solutions. All right, what else do you need? You need to be told, I told you you're going to be walking along it for a while and you're going to hop off. You need to be told how long to walk. We call that a step size. So you need the step size. Kind of like how many steps am I going to take? We call that either delta x is what I like. Some books will call it h, but you need to know how far to move over before you stop and readjust your tangent line. All right? To find that step size, it's one of two situations. Best case scenario, they give it to you. Like they just say, using a step size of 0.2, and you're like, all right, thank you. Right? But sometimes you're going to need to infer the step size. So I'm going to write infer, and I'll put an example of that. Then we just go do 2 and we call it a day, because it's not difficult if you get the pattern to it. So if they say that your initial point is maybe at 1,5, and then it says use Euler's, I'm not going to write method, I'm just going to write Euler's. Use Euler's with 4 steps of equal size to estimate f of 2. Then you need to infer the step, that should be quotation mark, sorry. Boom, you need to infer the step size. You're going to be at 1, you're going to estimate what happens at 2 in 4 steps. What's your step size? What is it? I can't hear you. 0.25. Yeah, a fourth. Exactly. For you to go from 1 to 2 in 4 steps. You can also go backwards, by the way. So that would be a delta x of 1/4. If I had said to estimate f of 0, then I'd still have a step size of 1/4, but I'd use a negative 1/4. So if you're going backwards from the start, what are you going to use as your step size? Negatives. So, but if it's not given to you, it'd be really easy to find. Like they'll give you a 2 and ask you to estimate what happens at 8, and they'll say using like 6 steps of equal size. Well, then I go by ones. So it'll be very easy. So we'll just go ahead and I'll give you how I would totally suggest you lay these out. It's not the quickest way. It's the way that you're going to remember, and it's safe. So I'm not giving you the fastest way to do these, which is with a strung out model where you just plug everything in, because you won't remember what you're plugging it into. So our goal is we're going to start at a given point. They will give you that. We are going to make a table. So the first thing I put on my table, go ahead and write this down, is a point that they give me. You will be handed that in your lap. Okay, and what you're going to say is, okay, what am I going to do from this given point? You're going to start walking along a tightrope that has this slope. So you will calculate the slope there. It'll be given. It might say dy dx equals x minus y squared. Well, then you'll just take whatever point you were given, plug it in, and you'll get a number here. Just for the heck of it, let's say that it ended up being 1/2. Okay, so you're walking at a fairly gradual uphill grade for a little while. Okay, how long? They'll tell me, or I will infer it. Maybe I'm to go from 1 to 2, right, in 4 steps. So I'll use a 4th. But this will be given, or you'll be told. The only thing that might mess with your head a little bit is, not only do you need to know how far over to go, but you need to know how far up to go. Okay? But you should know that the change in y over the change in x is the slope. Wouldn't you agree? So delta y is really just the product of the 2 you just found. So go like this and write multiply. Change in y is equal to the slope times change in x. Well, you will have just found the slope and just found the change in x. So in this scenario, my delta y would be 1/8. Make sense? Right? So I'm going to walk at a slope of 1/2 until I get to x is 1/4, at which time y will be 1/8, and then I'm going to stop. Okay, and I am going to halt production and say I need to readjust my tangent line. Where do I need to readjust it from? Let's pretend there was a given point here. Let's say 0, 5. Okay, that was what they gave me. Walking at a slope of 1/2 until I've gone over 1/4, at which point I will have gone up 1/8 and I will be at a new point. My new point will be where I started, which is 0, plus my delta x. My new y coordinate will be where I started, which was 5, plus my delta y, and I'd be at 5 1/8. And you might say, then what? Well, then you start all over, and you say, okay, I'm going to get off that tangent line right now, and I'm going to hop onto a new one. And that new one will have a slope of, and now you plug it in again, and you keep going through it. So it's all about hopping on tangent lines and then getting off and recalculating, instead of just going like this the whole time. So let's go do one. I think on yours this says a 3, and because we aren't going to use calculators, it gets a little messy cubing decimals. So I want you to change that to a 2. So you'll know when to use this. It's super clear on the AP exam because they have to tell you to use Euler's. And tomorrow we're going to talk about Euler's in multiple choice and in FRQs. For today, it's just straight up do it. It says, using Euler's method with a step size of 0.3. Thank you. I told you most of the time they hand that to you. Some of the times you need to infer it. Find the approximate y value when x is 0.9. Okay, so here it says, it gives me the derivative anywhere on the curve. It says it's x squared. That's always given to you. They also handed me my initial point of 0, 1. You've done this before. You've solved a differential equation. We're not solving them today. We're using Euler's method to approximate what's going to happen when I get to 0.9. Question mark is my answer. All right, here we go. Try not to memorize or look at the table because you won't have it for tests. You're going to go like this. How does this work? You're going to go, all right, I need to hop on at this point. So go ahead and put that on there. I'm going to walk along a tightrope with this slope. I'm going to walk as long as they tell me to, which was delta x. That's how far over I'm going to go. Once I stop, I'm going to figure out how far up I went, which is delta y. How did I tell you you get delta y? Because that's the only one you really have to, you multiply these two. So I'll put a little asterisk there for times. Okay, at that point, I'm going to say, okay, get off the line. I'm going to be at a new point and I'm going to adjust. So right here, you will be at a new point where I add how far I went over to the x and how far I went up for the y. How long do you do that? Until you get here. You're going to walk. Okay, so basically you're going to be taking steps of 0.3. This never changes, by the way, in your table. I'm going to move over 0.3, move over 0.3, correct? You can actually get part of it right now, but let's just hop on. I'm going to hop on at 0, 1. What am I going to do? Walk, right? With a slope that's equal to only the x dependent, so x squared. I'm going to walk straight across, actually. Do you see what I'm doing? I'm walking like this for a little bit, but then I'm going to stop because there's going to be there's going to start being a gap with my parabola, and I'm going to adjust for that. If my parabola opens up, I'm going to tweak and start going a little steeper. Do you see what I'm trying to give you? You're nodding. I think you get it. All right. So what will y be? Well, 0, because the slope is 0. So I'm just going to be walking straight across for a while. It should make sense to why y won't change. I'm walking along a horizontal line. Are you good with that? So where am I when I'm done with that first step? I will have moved over 0.3, so I'll be at 0 plus 0.3, but I won't have moved up at all. Now what do? I stop, and I say, don't keep walking like that. If this is the parabola, what I'm saying is stop. Don't keep going like that. Tweak it, right? That's really what I'm going to do right now. So I'm at 0.3, comma 1, and I have a new dy dx. How do I find it? The math is easy. The math in Euler's is about as easy as math gets, for the most part, except I did have a funny question last hour. I'll tell you when I'm done. All right, I need to square the x. 0.3 times 0.3, watch your decimals. What is it? 0.9? 0.09. The decimal issues in here. That's actually, so I'll tell you right now, at the end of second hour, I said, so are there any questions? How do you multiply decimals? I'm like, are you kidding me? Everything I just told you about Euler and about the sine wave and a polynomial wrapping around it, and you're walking on tight ropes, and you asked me how to multiply decimals. So I stopped and I said, you multiply decimals as if they are not there, right? So let's make it nicer. So if you were doing 1.02 times 0.8, you pretend they're not there, and then you scoot over the number of decimal places to the right. If you forgot that from the 3rd grade, it needs to come back because you won't have a calculator and you have to do it by hand. And honestly, on the FRQs, that's where you're going to get it wrong, is the little details of it. So 0.09 goes right here. How far over am I going to walk? All the time. How far up will I have gone? Well, now I'm not walking on a horizontal line anymore. So the change in y is the slope times change in x. When I multiply these without the decimals, I get 27, but I have to scoop over 3.027. Where am I going to stop now and adjust? Well, where am I going to stop? Where will I now be? Point what? 6, exactly, and 1.027, exactly. I'm just saying, okay, I was at 0.3, going forward 0.3, I'll be at 0.6. I was at 1, going up 1.027 will be where I am sitting. What does that mean? It means that's where I'm standing right now waiting for a new tightrope, because I'm going to adjust my slope now again. So what do? It says, along the curve, the slopes, you square the x value. So I square 0.6, which gives me 0.36. My delta x never changes. They told me 3 equal step sizes. I multiply those as if the decimals aren't there, carry the 1, and then I scoot over 3. Now where am I? After those 2 moves of 0.3 to the right and 0.108 up, where am I? 0.9, and now I have to do some decimal addition here. 5, carry the 1, 3, 1, 1. Boom. What's the answer to this question? Yes, we are estimating the y value. So the y value at 0.9 is about 1.135. Is that exactly what it is? No. Is it way better than Calc 1's singular tangent line? Oh yeah, way better. Could it be better with this process? How could I make my approximation better? Take more steps and smaller steps. And they've now, since the age of computers, now this is a computer algorithm, so nobody really who would do it in the real world, like if they had a Diffie-Q they couldn't solve and couldn't fit a polynomial to it and had to estimate how much of something was there at some time, they actually wouldn't go through this process, because you could find a computer program. You could program the graphing calculator. It's probably fairly easy to do it because it's so iterative. What does that word mean? You don't know that word? Oh, vocabulary lesson. What does it mean to iterate something? Repeat it. Yeah, it just does it over and over. The same process over and over. So last one up. It says for the previous example, I could actually tell you how far off it was because I gave you an initial Diffie-Q that we know the solution to. Why would we use Euler's for this? I can get an equation for the curve, so I know exactly what's happening everywhere on the curve. The y values are equal to x cubed over 3 plus Carl. I already know that. So that was a stupid problem. But I wanted to show the process, right? The minute my Diffie-Q became this, x squared plus y, then I'm stuck. But this one I could do easily. I knew, what was the point? Was it through 0, 1? Yeah, so I know Carl has to be what? 1. Somebody take out their calculator for me who's got one out real quick. Anyone have their graphing calculator out? Do me a solid. And we'll go see exactly what y of 0.9 is because I have the exact curve. So no need for Euler's. I got this, right? Somebody take out a, thank you. Thank you, Cole. 0.9 to the third divided by 3 plus 1. It's going to be 1 point because my approximation was 1 point. 243. What was our approximation again? 1.135. So it says, what's the error? I'd subtract those. Right? Mine was under, so it'd actually be considered a negative error, right? I was a little below what it would be. But again, I asked, how could you make it better? And Addie said, take more steps, right? So I could, actually, that's pretty good for only 3 big steps. It's way better than last year's. So I won't finish this whole one. I think you need to add 2x and then the minus y. Now, you guys have been with me for a long time. What do you think? You know what annoys me. What do you think annoys me about Euler's method? What do you think annoys me about it? In the process, what do you end up having to do? Arithmetic. Not my favorite, right? The process itself is cool. I like doing it. And because I'm the teacher, I don't really have to do the arithmetic. So I'm not going to on this one. Because I don't want to. Could I, if someone put a gun to my head? Yes. Am I going to? No. All right, so I'm going to have you change the diffie-q to a little more ugly one that you actually couldn't figure out exactly what's happening. I have no clue what the original curve was with any methods from Calc 1 or Calc 2. I cannot figure out how to solve that for a y. I can't separate because of the minus in there, so I am stuck for now. All right, so what am I going to do? I'm going to get an estimate, but I'll use Euler's method, and here's the kicker. 4 equal steps, and I'm going backwards because they gave me the 0.2 comma 3, and when I'm done, I want 1.6 comma. Question mark is my answer, right? Question mark will be an approximation. Agreed? All right, so when I start making my table, I start, and I hopefully don't need to have it memorized. If you do it this way, you'll retain it. All right, so when I make my table, what's the first thing I do? I put my point down. I need to hop on the curve, basically. If you understand the process, there's no memorizing. Once I hop on there at 2, 3, what do? So I hop on the curve at 2, 3. I can't see the curve. I don't know an equation for the curve, but I know I'm hopping on it at 2, 3, and what am I doing? Yeah, well, I'm going to, but my first step, I need to know how steep am I, what tightrope do you want me to walk on? I find the derivative there, and I start to walk. Correct? I start to walk until I've gone over what they say, because I need to take 4 equal steps to get from here to here. What's my step size? Nope. 4 equal steps to go a distance of 0.4 would be what? What would it be? 0.1, right? But what's wrong with saying 0.1? Yeah, that will send me forwards from 2 to 2.1 to 2.3 to 2.4. I want to go backwards. So I had to infer delta x on this one. Once I figured both of those out, I need to know how far up to go. And I'll go up there, and I'll stop and say, time to tweak my tangent line. So I'm just going to put new point right here. So here's the structure. You shouldn't forget it if you get what you're doing. So first thing up, I will go find dy dx. How do I do that? Twice the x minus the y. That's going to give me 1. What's the change in y going to be? Slope times change in x, so negative 0.1. Where will I now be standing waiting to hop on a new tangent line? I was at 2. And where am I going to be standing now? 1.9. I went back 1 step. Well, I went forward a negative step size, if that makes sense. And then how about my new point over here? 2.9. What does that mean I do right there? I do the whole process over again. I hop to that point, and then I tweak the slope of the curve right below it or above it. It depends on where I'm sitting. I'm actually right below. And I'm going to do my new slope. How would I find that? I'm just going to put a box there because I don't want to do the arithmetic. Could I? Yes. I don't want to. Are you all right with me just bailing on the arithmetic? What goes in here for sure? Negative 0.1. How would I find delta y if I was in the mood to do arithmetic? And multiply these two. I'm going to call it a triangle because I don't want to multiply them. All right? So what would my new point be once I was done with the arithmetic that I hate in it? 1.8, right, comma, 2.9 plus the triangle. All right? And when I'm done, I would do it again and it'd be at 1.7. I'd do it again and it'd be at 1.6. My answer is right in this blob. That is my approximation. So ignoring the triangles and the blobs and the rectangles, do we understand the process? Okay? Do you understand why I didn't make them? I'd still be over here working with my decimals. I don't want to. So for the homework, you should finish it. It goes really quickly. There's only 7 of them. The answers are on the back. I'm going to let you cross off. There's one of them where it says to sketch, and you don't need to do this sketch. That I took care of showing you graphically what was happening. So, 1.6 blob is the answer. After you do 2.9 plus triangle, we get 1.6 blobs. All right, so on number 1, you can cross off in 1A, cross off the sketch your solution part. I still want you to do Euler's method. I still want you to actually solve it because you can. That one you can easily integrate x plus 2 and, right, and find the error. I want you to look at, there's 2 on here that are very College Board. What do? They're brilliant. They know there's smart little peeps out there that make a computer program and a calculator program out there. They know you could Google TI-84 program for the Euler's method, link up and just copy it onto your calculator. It's out there. I have it on one of my calculators. It doesn't do me any good on the AP exam because what do? They brilliantly phrase it like 2 and 6. So even if it's on the calculator active portion, it's of no help to you because you have no clue who the function is. You have no clue what the derivative is as a expression. So let's look at number 2. They're easier if you understand the process, but for kids who just memorize a model, they're toast on number 2. So let's go look at it. Suppose a continuous function f and its derivative have the values given in the following table. Given that f of 2 equals 5, use Euler's method with, and they give you the step size. You could easily make a table from that information. What would be your starting xy? 2, 5. Okay. What would be your derivative that goes into your first thing? It would be the derivative there. What's the derivative at 2, 5? 0.4. What's delta x? That goes on my I need to know how far over to go. What is it? Because they handed it to me. What's delta y on my table? The product of the other 2 I wrote. Where am I now? Start over again. They're handing you everything. But if you don't understand what you're doing, adjusting, then that just looks like, what's the other one that's very College Board-y? 6. The other ones would be like out of our textbook. So I try to give you both. Tomorrow we're doing only College Board, but today both. All right, go ahead. That's due tomorrow. If you finish it today, I do have an empty-ish basket, so I'll take it. Answers are on the back. You just need to show your work probably on a separate sheet. Peace out.